Hi, thanks for joining me today. I've got a fun number theory problem from the 1969 International Mathematics Olympiad. This is problem 1. We want to prove that there are infinitely many natural numbers a with the following property. The number z equals n to the 4 plus a is not prime for any natural number n. Okay, so if you want to have a go at proving this, pause the video now and give it a go for yourself, and I'm going to dive straight into a solution. Okay, so before I dive into a solution, I just noticed that there's actually a small typo here in the problem. They've put the number 1 here and not the letter L. So a very small misprint there, but this is actually a screenshot from the original paper, so this went unnoticed, I guess. Anyway, hopefully that won't stop us from solving the problem. So we want to show that z equals n to the 4 plus a is not prime. And the easiest way to show a number is not prime is just by showing that it's the product of two positive integers which are bigger than 1. And now remember, we don't need to show that this is true for all a, we just need to show that it's true for infinitely many values of a. So we need to kind of choose a particular infinite class of values of a. And we have a play about with it, and we notice, or perhaps we arrive at, this choice here. So n to the 4 plus, and now a, I'm just going to say, is equal to 4 times k to the power of 4, where k is just some natural number. And obviously there are infinitely many choices for a then, just by making infinitely many choices of k. Now, all I want to do now is prove that this thing here is not prime, and I'm going to do that, as I say, by factorizing this thing. So how can we factorize this? And there's a trick to this. I'm going to add on 4n squared k squared, and then take it off again. So take it off over here. And what's quite nice about this is now secretly the difference of two squares. This is going to be n squared plus 2k squared all squared minus 2nk squared. So this thing here is going to give me this thing here, and this thing here is that thing there. So now it's the difference of two squares, so we can indeed factorize it. So it's going to be n squared plus 2k squared plus 2nk multiplied by n squared plus 2k squared minus 2nk. So now all we need to do is verify that both of these here are bigger than 1. And so firstly, let's notice that they're definitely both positive, because, well, the only one that could be negative is maybe this one, because it's got a negative sign there, and n and k are both positive. But if this was negative, then this would also have to be negative, because we know it equals this guy here, which is positive. But that's not possible, because this guy here is very clearly going to be positive. So that means that this is certainly, each of these brackets here are going to be positive. Now, this one here is clearly the smaller of the two, and so I need to check that this is bigger than 1, but the easiest way to do that is just by noticing that this bracket here is just the same thing as n minus k all squared plus k squared. And because I can insist that k is at least 2 if I wanted to, so k is at least 2, this thing here is going to be at least 4, and this thing here is going to be at least 0. So all in all, this is going to be strictly bigger than 1. And therefore, z is not prime, regardless of the value of n, when we choose a to be this value here, 4 times k to the 4. Anyway, that solves this problem. I hope you have enjoyed this quick solution video. If you are new to the channel, please do consider subscribing and checking out some of my other fun maths videos as well. Anyway, I'm going to stop waffling now. Thank you for watching. I'll catch you in the next one. Have a great day.